Hi everyone, this is 2022 AMC 10B number 20. So we have a really nice geometry problem, and I highly recommend you to try it first before you see the solution, at least one of the solutions. So we have a rhombus, okay, and then one of the angles is given. So let's actually go ahead and draw a rhombus. Okay, so I'm gonna make it something at least looks like a rhombus. Okay, let's assume this is my rhombus. And then ADC is 46. Since this is a lot less than like 90, so might be this guy or this guy, at least based on my figure. And I'll just take this guy as this angle. So if I want to get ADC for this guy, so D and D should be right here. So maybe A is right here. So A, B, C, and D. Okay. And then this is 46. But I'm gonna actually write it for now. That's 46. And there is a point E that's midpoint of CD. So it will be right here. That's E. And then let F the point on BE. Okay, there should be a segment from B to E. So let's connect those then. And then such that AF, okay, A to F is perpendicular to BE. So meaning that we do have another segment from A to that BE that will be 90 degrees with intersection of BE. Okay. So then I'll have, this is 90 degrees. And what's the angle measure of BFC? B, so this was F. So let's try, this is F. And we are basically looking for this guy. So based on my figure, so like I really didn't like this kind of lining because it looks like a straight line at some point, but it is not actually. So maybe I should take this a bit better looking. So I'm gonna take this guy a bit that way, so then I'll connect that way. Okay. So then this is 90 degrees, and this is point F, and this is C. So we are looking for BFC. So this is the angle actually we are looking for. Okay, so now let's look at what we can do, right? So we are told this is a rhombus, so maybe it's gonna be helpful. It should be helpful. So let's actually label those segments. So these guys are equal. And then we are told F is the midpoint. So I mean, E is the midpoint of DC. So I'm gonna take these two are equal to each other. So usually when you are given some midpoints, especially for some like quadrilaterals like rhombus, you probably like hunt for some similarity as well, because you know the ratio will be 1 to 1, maybe that will be just congruent, which is why it's good idea to extend those lines that will actually intersect at midpoint. So I'm going to take this point B and extend it on the other way. And I'll take the point A and extend through D, and they will have a intersection. So maybe I should have done this only that distance. I just want to make it like longer so you can see that when you extend AD, when you extend BE, they will have a intersection point at somewhere, okay? So which is right there. Anyway, so we have now this intersection. Let's call this is K, but you might be wondering why I did this one, because again, as I said, like this is equal to this guy, and then I just like to use that midpoint information. So that's why I just like to extend so I can maybe see some similarities, which is actually going on. So if you are familiar with the similar triangles, actually there is one immediately right here. So this triangle and this triangle are actually similar because, you know, the BC and AD are parallel because rhombus is also a parallelogram. So if that's parallel, so the angle right here, this guy, and the angle right here are alternate interior angles. And similar idea, so angle C right here, and then the exterior of this angle D is also alternate exterior and interior. So those two are also same. And then this angle right here and this angle right here are vertical. So meaning that BEC, so I'm gonna actually, yeah, let me write that. So BEC, the similar to, so KED. So KED. So you can maybe write this a bit different order, so that should be fine. And these guys are similar. And then when you add like by angle, because they share the same three angles, so two angles is more than enough. So now we know this angle K is opposite to DE. The corresponding angle on the triangle is opposite to EC, which is like the same segments in terms of their distance. The ratio of the scale of these two similar triangles is just 1, meaning that these are not just similar, they are actually congruent. So, and then this vertical angle is opposite to KD, the same angle right here opposite BC. So that means BC and KD should be the same as well. So then I'm gonna say this is also equal to one of those four sides of the rhombus, okay? So far so good, I guess. So, but here's what I'm gonna ask you to think about it carefully, or maybe ask yourself, you know about it. So, you know, AD is equal to KD, and then we have a right angle triangle right here, so AFK. I hope that reminds you something. If that doesn't remind you something, so let me kind of remind that for now. So if you have a right triangle, okay, so let's say we take that segment from the 90 degrees, and we divide this into two equal pieces. Okay, so if these two guys are equal when this is 90 degrees, then this segment will be actually the same as these two. And then there are a couple ways to prove this one, but since this is gonna be beyond the scope of this problem, so I'm not gonna dive into that right now, but it's good to know as well. So when you have a right triangle, okay, and if you connect the vertex, which is right angle vertex, to the midpoint of the hypotenuse, that distance will be actually the same as those two pieces, which is gonna be this one. Or if you are given a triangle, and then if they don't say this is 90, but they tell you those three are equal, then you can conclude this angle should be 90 degrees, okay? And that's something, and maybe at least we can see one way to make a reasoning why that's the case. So if you have a circle, I'm gonna make a diameter, and I'm gonna draw a triangle, okay? So this is actually one of the reasons why this is correct. So again, I don't know about this angle measure for now, at least, and I will connect that point to my center. So if I do that, let's say this is my center, A, B, and C. So since this is radius, these guys should be same, right? And if I call this is alpha, then this guy should be alpha because this is isosceles. And then if I call this is beta, then this is gonna be beta as well because these two guys are also equal. As you see in this triangle ABC, we have alpha, beta, beta, alpha, alpha, beta. So there are two of each. This is equal to 180 if you take the half. That means the alpha beta is add up to 90 degrees, which is actually the angle right here. So whenever you see a triangle actually share a vertex, like that vertex on the circumference of the circle, okay, if that angle is actually facing to diameter, which is in this case, that angle will be 90 degrees. And then this is just another way to think about it. So, and maybe if you are given a right triangle like this, you can actually make a circle around this triangle. And then sometimes we are gonna call these circum center, like the center will be circumcentered, or the circle will be circumscribed. Okay, so if I do this, I can actually make a circle that will be outside of that right angle triangle. Anyway, so you got my point, I hope. So these are just some background. You are gonna see why I'm gonna explain those in a second. Okay, so let's try now go back to problem. So you know, we have a right triangle, right? So AFK, and now we know AD and DK is the same, which is like this piece and this piece. And now we have a right triangle right here. So that means if you connect D to F, that will be actually our third segment, which is going to be equal to each other. So meaning that if you take this point as your center of a circle that has a radius of AD, that circle should be passing through this point, and this point F, okay? So let's try to see how that looks like, okay? And at the same time, not just those 2 points as well, you know, AD and DC are equal, so that means your like circle should be passing through actually these points, okay? So let's try drawing that circle. But make sure you really understand why that's the case before you move on. So again, it's not really perfect circle, but at least it will do the job. So I said the reason why we can do that, because I just take this guy as my center, and then let's assume we want to draw a circle that has a distance of AD. Since AD and DK is the same, and that's same as DC, and that is also the same as DF. So that means my circle should be passing through AFCK, okay? So now we have a circle, okay? So we can make a maybe a bit clear. Okay. And now I want you to remember the inscribed angle. So inscribed angle was a angle that is inside of a circle that is on the circumference. Okay. So for example, if you have two segments, which is we call chord, let's say this is my chord and this is another chord. So I didn't like that. Okay, let's say this is another chord. So the angle in between those two chords are right here is called inscribed angle. And then the angle, if I call this is alpha, the corresponding angles right here, it should be. Okay, I'm gonna do it in a different color. So the angle right here is called inscribed angle, and then the segments, no, not the segment actually, the arc that is actually facing to that inscribed angle is gonna be this piece, and that will be twice as big of this inscribed angle. And this is really important property of the angles in a circle. And I'm gonna use this guy in our problem as well. So, but make sure this is like what you are trying to find, right? The angle right here is what you wanna find. So BFC, maybe if I know the other side, which is like 180 minus this angle. So this is actually a inscribed angle. So if you don't really see it, so it's better to maybe make it a bit visual. So give me a second. So think about this is my one like chord, and let's take this as another chord. Okay. So and you know, if you can find this angle, that is gonna be half of the angle measure of this KC arc, right? So it's gonna be, maybe I should write that guy. So the angle measure of KFC is gonna be half of the arc measure of KC, okay? So then if you can find this guy somehow, then you can find this for sure. And what I'm gonna do actually, you know, we never use this angle, right? This was a angle in a isosceles triangle. Maybe it's good to use that, which is gonna be our next maybe hint. So if I connect A and C, because that was a isosceles triangle, if you subtract this from 180, you got like 130, 130, 136, 134, right? And then if that's the case, the half will be right here, which is gonna be 67. And the other half will be right here, which is also 67. But I don't really care about that part because this angle 67, like between KA and AC is actually facing to this KC, which is gonna be twice as big. So that should be 137. I mean, 134, okay? So then if this is 134, we know this guy was the half of this, KFC was the half of this, so which is actually 67. Then if the angle right here is 67, then the angle we are looking for is gonna be 113. And that is your answer. So again, this question, like if I want to summarize, basically testing you couple skills. First, inscribe angle. Second, as always, similar triangles. The third, this relation, which is sometimes, if you want to name it, like it's called like Thales theorem. So I don't know if you like to remember, but that's another the relation between the triangle and the circle. So you really want to remember all of these and apply in this problem. So it's kind of challenging because it's number 20, but at the same time, it's not that bad. Okay, I hope that makes sense, and I hope you learn something from this. Okay, so I'll see you next time.